welcome everybody right after lunch. It's always the hardest time. Everybody's tired and all the blood is in the stomach. But Jim and I, we're going to try to entertain you so that you stay awake. So we're going to talk about DaaS scalability and load distributions, the myths and the facts and the costs. And hey, Jim, would you just introduce yourself?
Sure thing. So my name is Jim Moyle. I'm a current CTP. I work for Microsoft. I used to work for FS Logics, but I do not have my Microsoft hat on today. All right. So I've got my community and math-based hat on today. So none of the things that I'm going to be talking about are officially Microsoft endorsed. I am not talking on Microsoft's behalf. This is purely personal. So I don't want to see any tweets saying Microsoft said this or that. This is purely a community session.
Okay, so it's always Jim says and not Microsoft says.
Yes.
Okay, good. Now about me. My name is Benny Tritch, and I also belong to several communities. I work for ControlUp part-time, and I'm the evangelist, technical evangelist for the German-speaking market. I also am a co-founder of Rex Analytics together with Christine Griffin. I contribute to Team RG and RDS Gurus. That's about me. Good. So I'm going to do the first part of this session, and I'm going to take us from the inside to the outside, and you will see what that means. And as soon as we are leaving the inside, Jim's going to take over. So this is the idea of this session over here. So when I look at our market, I try to look at it from a perspective of the end user. And this is very important because the end user is the relevant, person why we're doing all of that. So the perceived end user experience is the most important thing when this end user has access to any of the remoting environments, independently if it's on-prem or in the cloud. But unfortunately, there are these people, these other users, these noisy neighbors, and these primary users are constrained by the remoting protocol. They may be constrained by latency, but all kinds of factors out there. And this is what makes them unhappy every once in a while, because what defines user experience? And you see here log on time and graphics API support and the frame rate and user input delay, like the response time of the user interface. That's a very important aspect. The image quality and the multimedia performance, and also if the session and the applications are available all the time, or if they crash. So these are the most important factors for the user. But the problem is we do not have any real performance counter for user experience. Yes, I'm aware of the fact that some of the monitoring vendors, including ControlUp, they create that kind of performance counters or metrics, but they are collecting all the different performance counters and other metrics that they can find in the system to produce this kind of user experience score. But sometimes this is not enough. So, and the other question that we need to ask is, what happens if we add a GPU? Is it getting any better, or is it simply too expensive for the benefit that we get? Now, why would we add a GPU? I mean, typically application code runs on the CPU. CPUs get more and more cores, so most of the sequential stuff is being done on the CPU. But there is compute-intensive stuff that can be offloaded to the GPU. Sometimes it's only 5% of the code, but most of the times it's that kind of code that, does the heavy lifting in terms of graphics and in terms of encoding video streams, for example. And GPUs are optimized to do that. Okay, so that we know that GPUs are helpful, for what kind of user personas is that relevant? It's not so relevant for the task worker because it's fairly simple application. So it's good enough to have just a CPU, and the CPU renders the graphics and we're good. But as soon as you go to knowledge worker, info worker, or even power users, then those user personas can clearly benefit of a GPU. And I'm going to demonstrate that in a little bit. So what kind of VMs do we have for EUC in Azure? This is what Jim and I particularly looked at, and I also had great help from Christine Griffin. She ran a couple of tests over the last couple of days, and I'm going to present the results in only a couple of minutes. So the most popular machines that we see for EUC right now are the D4SV3 or D8SV3 types. And what I did is I put together the number of vCPUs they have, the RAM, and the price. And, the interesting thing is if you compare that to the GPU accelerated VMs, the NV6 powered by NVIDIA, or the NV version, the NV4 version 4s. So those are the ones that are powered by AMD. So the NV4AS, the NV8AS, the NV60AS V4, it's AMD CPU and AMD GPU. And it uses a new technology that was introduced, which is GPU partitioning, which allows you to cut the GPU, the physical GPU, into virtual pieces and assign those to the VM as if it was a physical GPU. So this is why we can assign half of an AMD GPU or a quarter of an AMD GPU or 1/8 to a single VM, including the video RAM, the frame buffer. And as you can see, this brings down the price massively. So if you compare the D4SV3 with the NV4AS V4, there is not so much different in price anymore. So it's almost the same. So both got 4 vCPUs, both have about the same amount of memory, but the NV4 adds a GPU. Okay, now let's look at a more beefy machine, the D8S V3. So again, if we compare it even to the NV16AS, so a much more powerful VM, the price is almost identical. And this is the information that we took to go into the details. What kind of benefits do we get if we start using those GPUs? So it's time for some action here. So we want to see what it does. Okay, so we built a Rex Analytics lab. And as you can imagine, we add an endpoint device. It's always a NUC that Christine and I are using to always use the same endpoint so that our results when we are doing the same test runs are comparable. And we connect, in this case, to a WVD VM or multiple WVD VMs. On those, we have installed Rex workloads and runbooks and personas. I will dig into that in a minute, and some tools that help us to collect the telemetry data. Yeah, and we have a video recording machine that we call Rex Tracker, and we record all the frame videos or the screen videos through a frame grabber. In addition, we have a tool that allows us to create the noisy neighbor load. We call that Rex Connector. This is all controlled by this central entity, the central machine, our lab controller basically, and there we are collecting all the data and we're writing the video files and the telemetry files to the storage. Good. Now, when we run those tests, we have a primary user, and the primary user uses the relatively short workloads between 45 and 120 seconds. And side by side, we're running the secondary users. They run up to 60 or 90 minutes. So they create a consistent load in the background so that we can run multiple foreground workloads in the primary user session and record the primary user session. But we are sure that it's fair, that the background load is always the same, no matter how long we wait. And just to give you an impression what those background workloads look like, here are 4 of these noisy neighbors running side by side. It's 4 separate sessions. We just recorded that for, well, demo purposes here. Typically, we never record those, so they just run in the background with the sessions open so that everything is rendered. So you see the users watching videos and interacting with applications, while using Office-like applications, watching images, and so on and so forth. Then we record the primary session, we feed the videos into the top quadrants. We can compare two different test runs with different requirements or different setups, and then we overlay the telemetry data in the lower part of the screen. I mean, if we look at that from well, an overview standpoint, so we have the video recording in the top quadrants, and we have the telemetry data we collected on the target session hosts in the lower level, the lower half of the user interface of Rex Analyzer. Good. Now we can run that and we can compare it side by side. We color code it like red and yellow or blue and red, something like that. So we can see the color coded telemetry data in the lower part of the user interface. Good. As I said, Christine, she collected most of the data here. She ran many of those tests, and I just want to walk you through some of the tests that we did. The first one is an NV6 with a GPU and with a disabled GPU. So what we did is we just deactivated the GPU on the same machine, and we ran the same tests. In this case, an Internet Explorer WebGL application, and now we run it. On the left side, it's with the GPU activated, on the right side, without the GPU. And I know that you cannot see the details through GoToWebinar for sure, but you can clearly see that the resolution on the right side is by far not as good as on the left side. It's real water on the left side, while it is, well, something that comes close to water, but is not really water on the right side, on the red side. But the red side consumes almost 100% of the CPU, while the blue side only like 10% of the CPU, while it is offloading most of the heavy lifting of the computer graphics to the GPU. So you see the GPUs only use 10%, but the offload is so massive for the CPU that it goes down from 90% to 10%. And you also see the CPU queue length that is heavily affected by that. And you see the RDP output. We can output a lot more frames per second on the blue side than we can on the red side. So this is the result number one that shows you the difference between GPU and no GPU. What we do now is we use the same machine, but we add the 4 noisy neighbors. So the 4 noisy neighbors are running in the background, again, GPU versus no GPU, with a different workload in the foreground. Now this is a heavy application, and you can see that the load was already at almost 100% for the CPU, but still by the help of the GPU for all the 5 sessions that are running simultaneously now, you see a wonderful rendering here with up to 200 frames per second on the left side, while it's only 1 or 2 frames on the right side, on the red side. And again, you see the RDP output. We have close to 30 frames per second on the left, while we have, well, like 1 frame per second on the right. Again, a huge difference from the perceived user experience. So this is something on the right side that makes users very unhappy if they have that kind of user experience. Now, we compare, again, the NV6. Now we have 4 versus 6 noisy neighbors. And we have, again, an Internet Explorer application that uses WebGL. And now we come to the limit because we only have 6 vCPUs in an NV6. And obviously, this is not enough anymore for 7 users because we have 6 noisy neighbors plus a primary user. So you see that the performance falls, is not as good anymore. And so it comes to the point where it's not acceptable anymore. So you see the frame rate goes down to like 20 frames per second, while on the left side, we can still render up to 60 frames per second. We even see, we have this color coding here that we're losing some of the telemetry data because the load is so heavy that we're struggling collecting the performance counter data, and we have a visualization now in our tool, in our Rex Analyzer, that shows us when we cannot collect that kind of data anymore, when it falls back to 0. In the past, we were always surprised about that kind of results. Now, what we do is we switch over to AMD and check out the NVV4, again with 4 noisy neighbors, GPU versus no GPU, and now we're using a real heavy DX11 application. And on the left side, as always, with the GPU, on the right side, without the GPU. And look at that, the application didn't even really start. And we are, without a GPU and the 4 noisy neighbors, we are at 100%. This CPU is hammered. And at the same time, the GPU is also at full capacity, but it takes forever without the GPU to load the application. So even though the GPU is at full capacity and does everything it cannot compensate for the lack of performance that it has when compared to a machine with a GPU, which is running smoothly. So it takes almost 45 seconds before the first frame can be rendered. And that is a massive difference between GPU and no GPU if you have some load on the system. And now the final one, which was the most spectacular one. We have no noisy neighbor on the left side and 4 noisy neighbors on the right side, in both cases with a GPU. Now look at that. We run this beautiful water simulation, and with a GPU and with the 4 noisy neighbor, the performance is almost identical. Yes, it puts some heavy load on the GPU, wonderful, but this is why it's here. Look at the CPU. The CPU is still at like 10%. So you see how much a GPU can do and how good it is, how beneficial it is in offloading all this heavy duty work from the CPU. So when we do a final price calculation from the numbers that I had initially, and we compare the D4S and D8S with the NV4 and NV16 V4, we find out that if we use the smaller machines for up to 4 users, so giving each of the user 1 CPU, 1 virtual CPU, we are in the sweet spot. And then we have a pricing that is around $77 down to $33 per user per month. And if we have a machine that is, well, more beefy, we can put up to 8 users on that box, because we found the sweet spot for the power user to be at 2 CPUs per user session and giving them enough GPU resources. So this is the sweet spot. And when we look at the numbers here, we are always in a range between like 80 and less than $30 per month per user session. This turns out to be the sweet spot if we're looking at this from the inside. And we have already recorded similar results in the past for IGEL. If you want to take a look at the video that we recorded for IGEL, go to RDS Gurus, take a look at the video. We want to convert the results that we collected, that Christine and I collected over the last couple of days and weeks, into similar videos so that you can watch them on YouTube. Wonderful. And this is where I want to hand it over to Jim. Jim, take the floor. The floor is yours.
Thanks, Benny. Can you make me presenter if that's okay?
Can I do that? Make presenter. Yes, I can. Do you want Jim or a presenter? Yes, you are presenter now. Take it away.
Excellent. So if I do that, and then that, can you see my screen, Benny?
Yes, I can see your screen.
Perfect. So Benny, you're just to get one thing from what you were just saying. With all the testing you've done, that sweet spot is somewhere between like 4 or 8 users per VM.
That is correct. That is sort of the sweet spot. We did testing with up to 24 noisy neighbors, but typically stuff fell apart. We had to use the largest VMs we could get. Very expensive VMs. So the best results were between 4 and like 12 users per VM. Yes.
Perfect. Thanks, Benny. Picture of me when I still had hair.
Yes, that was the time.
So we're also going to talk about identity in the same way that Benny has, but from a different point of view. We're going to talk about it from the underlying cloud fabric point of view. We're also going to talk about scaling. Now, people are very familiar with how scaling works. Okay, so you configure a buffer as a percentage of your total size, and then you know, maybe you could use a different setting for weekdays and weekends, so you don't have too many empty VMs running. And you could even use different settings for peak and off peak. But essentially, it's all about having enough VMs ready for your users, but not too many. Now, this scaling becomes really important in cloud because it's pay as you go, right? So if you're doing pay as you go, then you need to make sure you aren't running empty VMs as much as possible. So scaling gets a far more relevance when you're doing pay as you go in cloud than it would do otherwise. So scaling is also limited to your max concurrency. So let's give an example. So your usual concurrency is 600 users. Your max historical concurrency is 1,000 users. So as an admin looking at this data, you're like, okay, so my plan for concurrency, let's take a look at the max historical. Let's add a bit on top of that, so maybe 10%. So let's say our plan for concurrency, maximum concurrency is 1,100, and that should cope for that. So let's look at some real data. So this is 5,000 users over 1 week. This organization is slightly odd in that it doesn't force people to log off overnight, which is why you see it doesn't go down to 0 concurrency overnight. So people can keep a disconnected session for 24 hours, and over the weekends they force people to log off. You can see the dip in the middle of the days there for lunchtime. Now, if you're looking at this data, how do you say, okay, well, what scalability is needed? What's my maximum concurrency needed? How do I make sure that I'm prepared for the user load, but aren't spending too much money? So well, let's just take one day at a time and let's simplify this graph. All right, so let's maybe unsimplify it slightly. And we're back to our example of 600 users per day. This is a graph from midnight to midnight. So that's along the x-axis, so time along the x-axis, and y is number of users. And we can see that the area underneath the blue graph is users actually logged on, actually working. You can see that they come in at 8 a.m. and everybody's logged on over time by 9 a.m. So they take an hour each morning to log on, and everybody goes home at exactly the same second at 5 p.m. And we'll talk about that a bit more later on. Okay, so that's what you have normally. So this is your plan for maximum concurrency. So this is your 1,100 users. So this is actually what you need to cope with over and above what actually happens on a day-to-day basis. So you need to be able to scale up to this as quickly as possible. Now, depending on what solution you're using, what the control plane is, this is either going to be a power on of the VM or a creation of the VM. So whether it's power on or power on, power off, or create, destroy, then you need to be able to deploy and get those VMs ready for somebody to log on. There's two big differences here, right? Power on, power off means that you have to have actually created those VMs up front. So you need to have those 1,100 VMs sitting there, powered off to cope with your maximum concurrency. So you're paying for the storage while they're sitting there idle. And in fact, we've got 10% of VMs there, which historically are above past maximum concurrency. So that storage you may never use, that may just sit there idle. Create destroy then is by far the better solution. Well, we'll have a look at that because there is something around create destroy which has an issue, but we'll talk about that in a second. When I talk about deployment time, I don't care for this use case whether it's power on, power off, or create destroy. I'm just lumping all of that together and saying, okay, when you get your first signal, which is a user logon time, how long does it take to spin up extra capacity, whether it's power on or create, until that extra capacity is then ready for a new user to log on? If you have instant cloning, then you don't care about deployment time, right? And all of this is moot. Unfortunately, we do have deployment time, so this is now a consideration. Okay, so this is the same graph, all right? Midnight to midnight along the bottom. I know it's numbers and not time, but ignore that. All right, and we've got the same thing with 1,000 users this time. 8 a.m. to 9 p.m., 9 a.m. is when they log on. Then they work for the day, and then they all log off at exactly the same second. In an ideal world, what you have is this, right? So you have your buffer in blue on, ready for users to log on to. As soon as users start logging on, your scaling kicks in and you gain additional capacity. And then you have a set buffer during the day to make sure you can cope with anything else. And then you scale back down again overnight, all right? So for 1,000 users, 20% buffer, and a deployment speed of about 150 sessions per second. And we're talking about 10 sessions per VM here. Then this is perfect, right? This is exactly what you want to see. This is the ideal situation. But even in the ideal situation, right, the area underneath the orange compared to the area underneath the blue, you've still got VMs sitting empty a third of the time, just over a third of the time, compared to being used 2/3 of the time. This is something that you'd like to optimize. You want to get that empty down if possible, but hang on a minute, we were talking about the perfect situation. So what happens if it's less than perfect? And now instead of 150 sessions per second to deploy, it's now 30 sessions per second. And there is a slight difference in the steepness of these curves. But in order to not be in a situation where you do not have enough VMs for your users to log on to, the rate of deployment is crucial. And if your rate of deployment is slightly slower than your logon rate, then you have to keep an increased pool ready and empty for people to log on to. And it has a large consequence on cost, because we've gone from a 20% pool to just over a 40% buffer, just to account for that slight difference in rates of deployment compared to rates of logon. So it's still 1,000 users. And that is now 50-50 empty to logged on. Okay, so what if you got more users? Well, this at 150 sessions per second deployment speed, this was perfect for 1,000 users. We had no problems there. But now for 10,000 users, that deployment speed is so far off our logon speed that we have real trouble servicing that demand in time. So given that we can't service that demand in time, again, we need to raise up our buffer of available VMs that is permanently switched on, now above 60%, to be able to cope with our logon speed, our logon rate. I would actually love to see some data from the control-up guys as to what they see as logon rate in terms of larger organizations. Now over half we're paying for empty VMs. Nobody likes paying for empty VMs. If somebody comes to you and says, I've got this big cloud IaaS bill, what are we using these VMs for? Well, actually, 60% of the time, nothing. That's not a good story to be able to tell somebody. This is a question that's no longer on VDI Like a Pro. I wish it was still there. So this is an old, very old survey about density. People are talking about somewhere between 15 and 25. I think it's less than that now. Benny has just said that he likes somewhere between 4 and 12. The lower your density, all right, the bigger the problem this is, because your speed of deployment, although it says sessions per second, isn't actually, in a multi-session OS, isn't actually dependent on the amount of users. It's dependent on the amount of VMs, right? So the more users per VM, the better your deployment speed and the less you're going to suffer from this, okay? So bigger VMs better in terms of log on. Smaller density, looking better in terms of Benny's results, okay? So let's just assume for a moment we're going to do really big VMs, okay? And this will get us around these cloud API limits. Now I'm going to use an example from Azure, just because I work for Microsoft and I don't want to take anybody else's solution and pull them out and be mean to them. All APIs have a rate limit, every single one of them, okay? In Azure, you can see that it's for all per instance, per principal user ID per hour. And this is just for ARM. There are this a whole load of all the throttles and limits, and most of those are documented on the docs. You can actually see what they are as well. And that is, you can use a command to go and see what your limits are on a particular API. Not all are available, but there is a lot of them available. Okay. So now we know that big multi-session VMs are going to increase your rate of deployment. Yeah. And they're going to mean that you're going to save a lot of money on the front end because you don't have to keep as many VMs up and running as you would if you got small VMs. But what happens with big VMs at 5 p.m.? So let's just take 16 users per VM. The red box is a server, the blue square is a user. And now at 5 p.m. and you can see we've only got 16 users in our organization. Everybody logs off, everybody goes home, and then you switch the VM off. Well, in reality, everybody logs off randomly and not in much order. This is fine if you've got 16 users in your organization. Well, what if you've got 512 users? Let's say 5 o'clock starts. And what I'm doing here is I'm randomly, and this is properly random, I'm logging off users and they're going home. So it's a Wednesday evening, you know, some people have got stuff to finish, some people have already gone, 25% of users have now logged off. All right, still pretty full. So we got some more users logging off. This is all looking fine. And we're going to see that in a moment we'll end up with 50% of users gone. Now, I wonder how many people looking at this thought that we'd be able to switch a server off. I want you to make 2 guesses in your brain. How many users am I going to have to log off before the first server gets switched off? How many users am I going to log off before I can switch off half my servers? Let's carry on. So now the office is looking a bit emptier, you know, cleaners are starting to arrive. You're starting to think, I should really go home by now. And now we've got 75% gone, but we still haven't been able to switch off a single server. So let's log off some more users. Okay, 78% are gone. Now we can switch off our first server. Was that your guess, 78%? Was it bigger or lower? Let's keep logging off. Let's see how many people we've got to log off until we get to be able to switch off half our servers. Still not switched off half. Still not. All right, not many people left anymore. All right, 21 users left. We started with 512, we've got 21 left, which equates to 4% of the user population. So 96% before we can turn off half.
Jim, this is scary. How often did you run that?
I'll show you in a second.
Okay.
So So now it's Friday evening, and everybody's going home a lot faster. Because everybody wants to get to the pub. I would love to go to the pub. And this is a different pattern. This is a different randomization. And if you're asking me how I did it randomly, I wrote this slide in PowerShell. I didn't write it in PowerPoint. We get, instead of 21, we got 19 users left, same 4% of the population. So, and we'll wait for the last users to log off. We'll let them go home to their Friday night beer. All right, so 96%, those two simulations. Well, I ran this 100 times.
Okay.
And we see that this is the number of users left before we can switch off half, right? So we got 19 and 21 previously, so that looks fairly representative. So I did just run it 100 times for 16 users per server for 512 users. I wondered what happens if we change the density. So what happens if we have 256 users per server? So we got really big VMs. So we all know this wouldn't work, but we need about, well, 100% of our users to go home before we can do half of that. Half of that estate can switch on. Now, well, that doesn't make a lot of difference if we have 128 users per server. What if we halve it again? And now we got 60. That's still not making any difference. All right, well, let's half it again. Oh, that's not great, is it? Let's halve it again. Still 16 users per server. All right, and this is the result we got, right? 96% of people logging off before 50% can be turned off. Okay, so hopefully it'll get a lot better with 8 users per server. No, still pretty bad. How about with 4? We're starting to see some improvement. 2 and 1. So 1 makes a lot of sense, right? Because, you know, we can turn off 50% of our VMs when 50% leave. So, you know, it's VDI, it's single session. What this illustrates is it gets bad quick. Yeah. So even at 16 users per server, it's scary. So again, we're looking at low number of users per server, but we still have the problem with the 9 AM. So if you've got a large user population, then your deployment time comes into factor when you've got this low density. Now, I had a look at this curve and I thought, there's got to be a formula for this. So one of my colleagues created a formula, and it shows you how good the simulation was because that is the results of the formula. It matches up almost exactly. So I'll share with you that formula, right? So the problem, and this you can do for your environment. This you can work out for your users. This is how you do it, right? So the probability that the server is empty is equal to the probability of a single user being logged off. So if you look at your estate and at 9 PM, you'll notice that there's 5% of your user population still logged in, then your probability of a single user being not logged off is 0.95. U is the number of users per server. Okay, so now you know. So your probability of a server is empty, so let's call that 0.1. If you've got 10 servers, yeah, then 9 of them will still be logged on if your probability is E is 0.1. It was my colleague Angela Yang who came up with this, so I'm very thankful to her because I didn't have to do the work to get to such a lovely simple equation. Notice, by the way, that equation doesn't have total number of users. So it doesn't care whether you've got 100 or 100,000 users, this equation is still the same. So the next question everybody asks is, if you put it in drain mode, does that work? Nah, it doesn't really change anything. The only real thing that works is putting the hammer down on your users and telling them to log off and log back on again. Not a great user experience, but it's definitely going to help you with your cost. So there is some things like reserved instance pricing. All of this is
actually, I had the reserved instances pricing in my list, so that was part of my list. I thought that something like that would be coming.
Absolutely. So yeah, putting the hammer down on users is, or going single session, or doing reserved instances is the only way to fix this. What I might do is create a website and put the maths for the logging off multi-session and the maths for logging on, and effectively do a goal seek and allow you to plug in your numbers and get out an ideal density just from a cloud cost perspective. And then you can sort of give that as one way of deciding density, and then take Benny's look at deciding density, all about user experience, internal Windows resourcing, and then marry those two things up together, because you need to think about both the inside and the outside of this VM in order to get your proper density numbers to the right place.
Because in the end, you would need reserved instances with many users, because that's good, because you run them all the time. It doesn't really matter. You never turn them off. But if you have those dynamic VMs, you want to keep them small. And so it's all about mixing and matching the right VM types.
Yep. Yeah.
Good.
If anybody wants to follow up with me around the maths or wants the code or anything like that, then just let me know. Any questions that I need to be answering, by the way?
All right, if you have any questions, please ask them in the Q&A. There's an area called questions. All right, and I just invented a new way of collapse. We have a function as an attendee, which is called raise your hand. That will be our new collapse. All right, there's Benny, you can read out the questions if you think that this question is public enough. Oh, this works beautiful. This works beautiful. Look at the collapse.
Where are all those questions? I cannot find the question. Where is
well,
that?
The question is on the left-hand side, sorry, on the right-hand side, there's one of the tabs which is called questions. If you can enlarge that, it's both Jim and you should see the questions.
So there were some questions for you, Benny, earlier, which I answered, and I think there's no questions for me if I can see them.
Here it is. Here it is. Now
there
I can see. It's such a shame after 10 years. I don't know. Oh, migration tool. Yeah. Okay. Is there any math similar to the crazy setup load evaluator decide which server? So we're going to go through these questions offline and try to answer those. Can we have the PowerShell code? That was a question for you, Jim, I guess.
You absolutely can have the PowerShell code.
If it is,
all right. Yeah, if you want to take those questions offline, this is one of the great things of a web conference that you know, in real life you don't really have the ability normally right after the question after the session to ask the presenters, but here you do
one
have
of the things was, one of the questions was to keep the 20% buffer. Yeah, that is exactly what Jim pointed out. So we better keep the 20 or 30% as reserved instances, and then we only start the remaining 80 or 70% on demand. So this is the way to go. This should be fairly small VMs so that the users can log off fairly quickly, while the reserved instances, they can be larger and you can have 8 or 10 or 12 or 20 users on the box, and that should work. This is why you need to look at both the prices for reserved instances and pay as you go. This is it. Okay.
All right, there was a question which came up a couple of times. Can we have the source code of the PowerShell code? Well, I guess you guys accept major credit cards, right?
Sure.
Also pay by wire.
Jim will create a website, and then we're gonna get filthy rich. Yes.
Is that all it takes, Benny? Just creating a website and then you're filthy rich?
Yes.
Why has nobody else tried that?
It's so simple. Okay.
All right.
Thank you, everybody.
All right. All right. Do you want to answer a couple more questions before Andrew's session for those who are interested?
Let's see.
So there's an interesting question. Did you say the AMD instances also had AMD CPUs?
Oh, yes. There were, it's the EPIC 2 CPU, and it's outstanding because it comes with 64 physical cores. And this is the reason why those VMs based on the AMD CPU and GPU combo have so many available vCPU cores, because there are so many physical cores. And I know for a fact that Microsoft does not overcommit on the core side. So the Intel CPUs that are currently being used in Azure do not have that many cores, so not so many cores per VM, while with AMD, there are many more cores available for each VM. So instead of 6, we have 16 cores, which makes a huge difference if you want to have 2 vCPUs per user. So we have seen a very good performance with the AMD based VMs when putting our power users on them. So like you've seen, we can put 8 or 10 of these power users on each VM with half or a full AMD GPU easily. That's no problem. Yeah.
All right, another question. What about user anticipation? Surely many users will have a pattern how their week looks like. Maybe you can force users to work at the same expected time on the same machine.
What you can do is to ask them to use the same machine at the same time. But what we found out when we did some research in the market is that no user uses the same way day in, one day after the other. So if I look at myself, if I look at what I did yesterday on my computer, it's completely different of what I did the day before, and completely different of what I did the day before. So only the task workers, they like call center workers, they do exactly the same thing every day. Any other person, any other persona, it's completely unpredictable. So we cannot enforce that, not even for one user. So this is the reason why we cannot enforce it for an entire group within an organization or a specific persona across different organizations. This simply doesn't work. So we have to find like the average load, or sort of find out how many task worker personas, knowledge worker personas, power user personas work within an organization at a given time. So the statistics will solve it. And this is the only way how we can calculate the resource management and how good the perceived user experience is going to be. That's unfortunate, but human beings do not act in such a way that they do exactly the same one day after the other.
All right. All right. Well, thanks very much. All the remaining questions, they're still there. They are assigned to Benny now. And if necessary, he will answer you.
Thank you.
In private.
All righty.